In this video, we're going to discuss the quantum mechanical model of the atom. Now, the quantum mechanical model is one in a series of models that try to describe what is going on inside of an atom, how are electrons positioned around the nucleus. And the quantum mechanical model is the current and best model that we have today. Now, the quantum mechanical model builds on a concept that Niels Bohr predicted in his model of the atom. And it says that the energies of electrons are quantized. So that means that electrons in an atom are only allowed to have certain distinct energies, which means that they can have only certain distinct positions or orbits around an atom. Electrons are not allowed to exist in between these orbits. Now, the Niels Bohr model did a very good job of predicting the behavior of the hydrogen atom. But for larger atoms with more electrons, the Bohr model fell short. It could not describe the behavior of the electrons in these larger atoms. So a new and better model was needed. So in the 1920s, several scientists contributed to develop what is called the quantum mechanical model of the atom. Three major contributors that we'll discuss here are Werner Heisenberg, Louis de Broglie, and Erwin Schrodinger. Basically, and very briefly, Werner Heisenberg developed something called the Heisenberg-Uncertainty Principle. What this said is that we cannot know both the position and momentum of a particle at a given time. Now, applying this to an electron, what that means is that it is impossible to know precisely where an electron is and what path it follows. So unlike the Bohr model, where electrons were like planets orbiting around the sun, Heisenberg said that is impossible. We cannot know exactly where an electron is and its path. Now, Louis de Broglie, he built on something that Albert Einstein showed in the photoelectric effect. Einstein showed that light can have properties of particles called photons. De Broglie said then, well, particles could have the behavior of waves. So essentially applying this to electron, de Broglie suggested that electrons, which are very, very tiny quantum particles, electrons can have properties of particles, but also behave like waves, so have a wavelength and various things that are associated with waves. Now, Erwin Schrodinger, he used some new theoretical calculations to devise a mathematical equation that described the behavior of electrons in a hydrogen atom. The modern description of these electrons, what we now call the quantum mechanical model, is largely based on the mathematical equations and solutions for these Schrodinger equations. So a lot of the mathematical predictions and the mathematical descriptions of an electron are what we use today in our quantum mechanical model. So let's kind of sum this up and give an overview of the quantum mechanical model. The first point is that in the quantum mechanical model, the energy of electrons are quantized, which of course we know means that electrons can only exist in certain allowable locations around the nucleus. Now, this was predicted by the Bohr model and is still used today in the quantum mechanical model. The regions where electrons cannot exist are what we call nodes. Now, also, in the quantum mechanical model, electrons are not just particles, but also have properties of waves. So again, this came from de Broglie's predictions based on the de Broglie equations that he developed. So furthermore, the energy of the electrons is quantized. They can be thought of as particles and properties of waves. And furthermore, we cannot know with certainty the exact position of an electron in an atom. So the quantum mechanical model has a certain uncertainty associated with it, which of course comes from the Heisenberg uncertainty principle. So essentially, the region around the nucleus where there is a 95% probability of finding an electron is what we call an orbital. So if we look at this little picture here, the Bohr model might look something like this, where we have a very small dense nucleus and the electrons orbit around like planets around a sun. The quantum mechanical model says that this does not happen. Instead, the quantum mechanical model says that there's a probability. We don't know the position, but we know with some probability of that we can find an electron within a certain space around the nucleus. So if our nucleus is right in the center here, there's a 95% probability of finding an electron somewhere in this fuzzy cloud here. So this region around the nucleus where there's a probability of finding an electron is what we call an orbital. So electrons exist in these orbitals. Different orbitals have different distinct shapes, and we'll show you those shapes in just a minute. The orbitals, where the electrons are likely to be found, their shapes are specified by different letters, S, P, D, and F. Again, we'll show you these more in just a minute. And each orbital can hold a maximum of 2 electrons, according to the quantum mechanical model. So furthermore, a group of orbitals, electrons exist in orbitals, a group of orbitals of similar energy is what we call a subshell. So we can group similar orbitals into what we call a subshell. And then we can group similar subshells with similar energy, into what we call a shell. Each shell is given an N number. This is kind of like we saw in the Bohr model. And the energy of an electron or orbital increases as we get further from the nucleus. So electrons in the N equals 1 shell have lower energy. N equals 2, 3, 4 get higher and more energy as we get into a higher shell or N number. So let's look at these shells, subshells, and orbitals in a bit more detail. So the quantum mechanical model says that we have the first shell, or N equals 1 shell. The first shell contains 1 subshell, and the orbitals in that subshell are s orbitals. So we'll show you what an s orbital looks like in just a second. And there is 1 s orbital in the first shell. So an s orbital has a spherical shape, like you can see here. Again, if our nucleus is right in the center here, then this sphere around the nucleus is a probability, a region of 95% probability where we're likely to find an electron. So what about the second shell? So the second shell, or N equals 2 shell, contains 2 subshells. An S subshell, or S-type orbitals, and P subshell, or P-type orbitals. So when the first shell is full, electrons will go into the second shell where there's 2 subshells. We have S-shaped and P-shaped orbitals. There is 1 S-type orbital, and there are 3 P orbitals. So the second shell contains 1 s orbital and 3 p orbitals. We saw what the s orbital looks like. The p orbitals look like this. We have 3 of them, one along the x, y, and z axis. And again, these are regions of probability where we're likely to find an electron. Again, the nucleus would be right in the center here. So let's move on to the third shell. The third, or N equals 3 shell, contains 3 subshells. We have an s orbital, we have 3 p orbitals, and we have 5 d orbitals. So we have a sp and d subshell. The s subshell contains 1 s orbital, the p subshell contains 3 p orbitals, and the d subshell contains 5 d orbitals. The d orbitals, their shape gets a little crazier here. You can see we have 1, 2, 3, 4, 5 d orbitals, and the nucleus would be right in the center here. And again, the orbitals represent regions of space around the nucleus where there's a 95% probability that we can find an electron. So let's go on and try a few more. Look at the fourth shell. Again, as we get further from the nucleus, we get higher energy orbitals and higher energy electrons. The fourth shell contains 4 subshells. We have an s subshell, which contains 1 s orbital. We have a p subshell, which contains 3 p orbitals. We have a d subshell, which contains 5 d orbitals. And we have an F subshell, which contains 7 F orbitals. So the fourth n equals fourth shell contains 4 subshells, and you can see the number of orbitals here. Now, in addition, it also, an electron that has is in the fourth shell, or an atom which has a fourth shell, also has a first, second, and third shell. So what do these F orbitals look like? Well, we have 1, 2, 3, 4, 5, 6, 7 F orbitals, and you can see their shapes here. You don't need to memorize these, but the F orbitals represent regions where there's a 95% probability of finding an electron around the nucleus. And finally, let's look at one more. In the fifth shell, the fifth shell will contain 5 subshells. We have an S subshell, which contains 1 s orbital. We have a P subshell, which contains 3 p orbitals. We have a D subshell, which contains 5 d orbitals, an F subshell, which contains 7 f orbitals, and a G subshell, which contains 9 g orbitals. Now, we're not going to get into the shapes of the g orbitals, but please be aware of the, for each shell, how many subshells and how many orbitals we have for each of those for the quantum mechanical model. We're going to use these numbers and these orbitals when we start looking at electron configuration. So be sure you're comfortable with the quantum mechanical model and the number of shells, subshells, etc. for an atom.